In this module, we will discuss electromechanical actuators. In the previous module, we introduced electromechanical systems, and in particular looked at sensors as an example of electromechanical systems. In this module, we will look specifically at electromechanical actuators. We will first look at solenoids, then we will look at DC motors in quite a bit of detail, generating their mathematical models, discussing how they're controlled, etc. And then we will close with a brief discussion of a few types of AC motors, but we will talk mostly at a conceptual level and won't get too much into the mathematical details. Many electromagnetic actuators employ electromagnetic induction. In this sense, the actuator converts electricity into a force or a torque. Examples include solenoids, speakers, and electric motors. The basis for this is a physical law called Lorenz's law, which says that a current-carrying conductor in a magnetic field generates a force. And this works on the same sorts of principles we discussed previously with sensors. Current flowing through a conductor generates a magnetic field, and then that magnetic field can interact with the external magnetic field to create a force. One example of an electromagnetic actuator that's very common is the solenoid. And the way that it works is it has a coil of wire, and the current flowing through that coil generates a magnetic field. And so when this switch is closed, current flows through the coil and it generates a magnetic field represented by these dashed lines. This magnetic field then imparts a force on this iron core, causing it to move, in this example, downward. When the switch is released, causing current to stop flowing through the coil, the magnetic field disappears and the iron core is returned to its original position by a spring. This sort of actuator has many applications. It's used as a valve or a switch. For example, your door lock switch, you press a button and the door locks. That's most likely a solenoid actuator. Another example is a car starter. This is also the same principle on which a speaker works on, except with a speaker you have sort of a cone attached to the core, and by varying the current through the coil, the force acting on the core, which is attached to a cone, its movement changes, generating different amounts of noise, sound. Another very important example of an electromagnetic actuator is a DC motor. And again, it works on the basis of Lorenz's law, where current moving through a conductor in a magnetic field induces a force. And this is the mathematical representation of Lorenz's law. The force is equal to the cross product of the current and the magnetic field. Over here we have a simplified diagram of a DC motor, and you can get a sense of how it works. So there's a circuit that's attached to a voltage source, a battery, or whatever. It's a DC motor, it's a DC source. DC stands for direct current, so the current always flows sort of in the same direction with a constant voltage. And so the current flows through this circuit, and you can imagine, that's the direction of the current. There's a magnet surrounding this circuit, generating a magnetic field whose direction is indicated by these light blue lines. So this is the direction of I, that's the direction of B. This cross product you can determine the direction of the result using the right-hand rule. So you cross the current vector with the magnetic field vector, and the force will push down. So on this little segment of wire, there'll be a force pushing it down. As the current flows around the circuit, on this side of the circuit, the current is now flowing the opposite direction. So when you do the cross product, when you do the right-hand rule, the resulting force will push in the opposite direction, and it will be up. And so you have this coil where one side is being pushed down and the other side is being pulled up, and it'll cause it to rotate. And that's the basic notion of how a DC motor works. There's a couple challenges that arise, however. You can imagine that as these forces cause the rotor, causes this coil to flip, when it flips to the other side, this side of the coil is now over here. And so you can see that the direction of the current will be opposite the direction that it originally was. And that will cause the forces to switch. And you could imagine that it would want to make the coil flip back in the opposite direction. And so you wouldn't end up with a motor that's continuously spinning. In essence, the alternation of the forces would cause the coil in the middle to reach some equilibrium where it's basically just standing still. And so the way that this is addressed is that when the coil flips over, we need to switch the direction that the current is flowing through the coil. And that's accomplished with what we call a commutator right here. So this is sort of broken half rings, such that when the motor coil flips, this side is no longer attached to this side of the battery. Rather, it's attached to the negative side of the battery, and that in essence causes the electricity to switch directions, keeping the force and the resulting torque always in the same direction. So it's pushing down. When it flips over, the current switches direction, so it continues to push down. That will keep the motor spinning in the same direction. Another challenge with a DC motor is that in essence we're trying to get electricity to this thing that's spinning. So you could imagine if we had a sort of a solid physical connection, you could imagine the wires getting tangled up as it spins, as it continues to spin. And so the way that this is addressed is that DC motors include brushes. So this electrical connection here between the battery and the commutator, there are little wire brushes that slide along the commutator such that you're able to get the electrical connection, but you're still able to have the coil rotate. So that's very quickly the basic idea of how a DC motor works. The parts that make up the motor include the stator, which is the stationary part of the motor. The most important part of that is the magnet, as shown here. So this magnet is a permanent magnet, and it doesn't move, it's fixed. The part in the middle that's spinning, the spinning coil, is called the rotor. It's the rotating part. It's also called the armature. And then this part that causes the current to switch direction, these half rings, is called the commutator, and it connects to the current source through little brushes. Here's a little animation to try and further illustrate what we were showing in the previous slide. So as it spins, the current is flowing in one direction. The magnetic field is constant in its direction. This light blue represents the commutator. So as it spins around, there's a break in the commutation, and it stops the current from flowing, and then when it reconnects, the current is flowing in the opposite direction. When there's this break, there's no current flowing through the rotor, and so there's no force being generated. But the rotor continues to rotate because of sort of the momentum, the inertia of the rotor. And so it'll continue to rotate in the direction it was going until the commutator reconnects on the other side. So in the previous example, we had a very simple sort of schematic or example of a DC motor, just to try and give you a sense of how it works, of the underlying physical principles that make the DC motor work. This example, this picture, shows a little bit more realistic version of a DC motor, how one might actually look in practice. So in the previous example, we basically only had two magnets, a magnet with a north pole pointing towards the center of the motor, and a magnet with its south pole pointing towards the middle of the motor. This DC motor is what we call a four-pole motor because it has four magnets. It has two magnets with their north pole pointing towards the middle and two magnets with their south pole pointing towards the middle. And these four magnets interact to create these magnetic fields shown by these dashed lines. In addition, in the previous example, we had a single coil, a single length of wire. In reality, a real motor, a real DC motor, is going to have multiple coil windings, and you can see that here, where the dot shows that the current is coming sort of out of the page. The X is the current sort of going into the page, where each dot will be matched up with an X on the other side. And the examples where there's no current flowing at all, you can imagine that's where the commutator is in its break, so no current is flowing through the coil at all. The reason we use multiple coils and multiple magnetic pairs is to ensure that the current carrying wire is near a magnet for a higher proportion of time. And this will generate more torque, the wire being close to the magnet, there being multiple coils. So there's higher torque, and it also generates less cogging, which means the motor will move more smoothly. It won't be jerky. It'll flow smoothly. Here's a picture of a representative motor, and you can see here is the rotor where there's multiple sort of windings. And over here is the commutator, and you can see again that there's breaks in between each of the sort of wires, so that as it spins and reconnects, the current will change the direction that it's flowing. Real motors also wrap the armature around an iron core, and the reason that it does that is so that the magnetic field doesn't have to cross a large air gap. Crossing a large air gap weakens the magnetic field. So in this case, you have the coils wrapped around an iron core, which helps to keep the field stronger. And that's also shown here, where the coils are wrapped around this iron core. Here's another picture of a realistic and actual DC motor. And in general, there's two approaches to control the DC motor. We're in essence trying to control the torque or the force acting on the rotor, which will affect how fast the motor spins, how much torque the motor generates. Looking at Lorenz's law, the strength of the force is affected by basically two things: the amount of current and the strength of the magnetic field. And so those are basically our two options for controlling the motor, either affecting current or affecting the magnetic field. Controlling the motor by affecting current is called armature control. So we change the torque by changing the current in the armature. The alternative, affecting the magnetic field, is called field control. And so in order to do that, the magnetic field needs to be generated by an electromagnet. If we had a permanent magnet, you can't change the strength of the magnetic field. So we need an electromagnet, and that's what's shown here. So here's the rotor with its coils, its armature, and then here these coils represent the magnetic field. So by changing the current through this coil, we can affect the strength of the magnetic field. So in these approaches and in this picture, we have what's called a separately excited motor. The circuit for the armature is separate from the circuit for the field, and so we can control them independently. And in fact, we can actually combine armature control and field control in the same motor. Cheaper versions of a motor may not have separate circuits for the field and the armature. They may have the armature circuit and the field circuit in series, or they may have them in parallel. And so in that sense, we can't control the two independently. That makes speed control and torque control of a DC motor more difficult and less precise. So that sort of approach may be sufficient for a cheaper motor, for example a starter motor, but it's not something you would want to do for a more expensive motor or a more important motor, like for example a traction motor used for driving a vehicle. So far we've examined the underlying physical principles of how a DC motor works. Now we would like to actually generate a mathematical model of the DC motor, either a dynamic model or a static model. We're going to do that first for an armature controlled DC motor. So here is a schematic of such a motor where the current through the armature is affected with this voltage source, and the magnetic field is fixed either with a permanent magnet or an electromagnet with a fixed voltage and current. In order to generate this mathematical model, we need to sort of make some simplifying assumptions. One simplification that we do is to employ a lumped parameter model. So this circuit represents the armature or the rotor of the motor. And as you recall, physically it's a coil of many windings of wire. And so there wasn't literally a resistor and an inductor within the motor, but we can take that long length of wire and we can capture its resistance properties in a single parameter RA and a single inductance parameter LA. We can similarly do the same sort of thing with the mechanical portion of the motor. So the spinning rotor has some inertia, some rotational inertia, and the spinning of the rotor, the rubbing of the brushes, things like that, cause friction. And so we lump all of the inertia of the rotor in a single parameter J, and all of the friction of the motor in a single parameter B, which we'll think of as a damping coefficient, a viscous friction coefficient. Thinking back again to how the motor works, from Lorentz's law we know that the force generated on the rotor is a function of the current through the armature and the strength of the magnetic field B. Also thinking of how a force acting at a distance, or a force with a moment arm, generates a torque, we can come up with an equation for the torque being generated by the motor or applied to the rotor, where this constant K basically is based on the geometry of the motor, the number of coils, the position of the coils relative to the magnetic field. And since we're dealing with an armature controlled motor, the magnetic field is also constant. And so we can lump these two constants K1 and B into a single constant K, which we call the motor torque constant. And so the torque generated by the motor is proportional to the current through the armature with some proportionality constant K, which depends on the geometry and the strength of the magnetic field. From Faraday's law, we also generate this relationship for what we call the back EMF. And so if you think back to our discussion of sensors, you may remember that a conductor moving through a magnetic field can have an EMF induced, or can have current induced in the conductor. And so that's what we have here. The fact that this rotor, this piece of wire, is moving through a magnetic field induces an EMF or a voltage in it that's proportional to how fast the conductor is moving. So it's proportional to how fast the rotor is spinning. And we call it a back EMF because in general, most of the time, the EMF that's induced is in the opposite direction of the externally applied voltage. And this K sub B is called the back EMF constant. If you're in a situation where the units of the two Ks, the K and the K sub B, are consistent, the motor torque constant and the back EMF constant are equal. That's a little unintuitive, but it's sort of an interesting result. In order to generate a mathematical model of an armature-controlled DC motor, we'll need to use those relationships on the previous slide from Lorentz's law and Faraday's law, but we also need to be able to model the electrical aspects of the motor and the mechanical aspects of the motor. And so in order to do that, we can use the same sorts of approaches we used previously in the semester when we were modeling purely mechanical systems and purely electrical systems. So starting with the electrical domain, the electrical part of the motor, we have this armature circuit, and think back to how we might model a circuit such as this. We can in essence apply Kirchhoff's voltage law or Kirchhoff's loop law. And this is the result. And where this came from, if you think back, we start at one point in the circuit. As we go around the circuit, we pass through the voltage source. That causes an increase in the voltage. We have a bump in voltage across that voltage source, E sub A. And then as we go across the resistor, we drop voltage according to Ohm's law. So we drop voltage according to the product of the resistance and the current through the resistor. Then we drop voltage across the inductor, where the voltage drop is proportional to the rate at which the current is changing. Then we drop across the rotor due to the back EMF, at which point we're back where we started. And so, since voltage is a potential difference, the voltage around a circuit, the difference in voltage between a point and the same point is 0. So that brings us there. We can also model the mechanical domain of the motor, the mechanical aspects of the motor. So again, thinking back to earlier lectures, think about how we might model the mechanical aspects of the motor. In essence, we can apply Newton's laws or Euler's laws. So we have this single inertia. We can draw a free body diagram and then write the equation of motion as sum of the moments equals J alpha. So in this case, if we look at this inertia, the torques or moments acting on the inertia are the torque generated by the motor, T, and then there's a resistance torque due to the friction. And so we model that friction in this manner. And in this case, we're modeling the friction as viscous friction, where the friction is proportional to the speed of the motor, or the speed at which the rotor is rotating. So these are the sum of the moments, and it equals J alpha, where angular acceleration is theta double dot, and J is the rotational inertia of the rotor. These two equations are then coupled by the previous relationships we had on the previous slide. So this is a completely electrical equation, but if you think back to back EMF depends on the mechanical speed of the rotor. So the electrical domain is coupled to the mechanical domain through the back EMF. Similarly, this is a mechanical equation, but the mechanical torque that's applied to the rotor is a function of the electrical current. where the motor torque is equal to the motor torque constant times the current through the armature. In this class, when we have to model electromechanical systems, I will expect you to be able to generate the equations for the electrical domain and the mechanical domain using the approaches we've learned previously. However, the sort of electromagnetic induction relationships I will give you. So for example, the relationship for back EMF, the relationship for motor torque, I will provide you. Similarly, if I gave you a speaker or a solenoid or a sensor or something like that to model, I would again give you these coupling relationships, these electromagnetic inductive relationships.